Peter Hill Explains, where I invite you to join the science teaching conversation with me about muons. Now, these are heavy electrons which pour in, not from outer space, but from the outer space, high energy particles hitting the atmosphere and showering us with muons. And a little voice in the back of my head said, oh, look, I should perhaps talk about them, because I've a lot of times said that, or just recently in a chat about mass, said that things are made out of generally protons, neutrons and electrons. That's what ordinary matter is made out of, and you very rarely get anything else besides that unless you happen to be in the have your stomach in the middle of the super collider in CERN. But the example that was sort of itching in the back of my head was muons, and they shower down from the top of the atmosphere on towards us at a rate, I hear 10,000 per square metre per second, and sometimes I hear other rates this size. One goes through your coffee cup every second in terms of going through it. Now, muons are heavy electrons. They're something called leptons. They're fundamental particles. They don't actually have any structure to them, and quantum physics sort of loves that sort of thing in terms of the heavier something is, the lighter it is. So in terms of a electron weighs in terms of 0.05% of a proton, whereas a muon weighs 10% of a proton. So that's a massive increase, a factor of 200 times more heavy. So an electron is a 2,000th, roughly speaking, the weight of a proton, whereas a muon, which is a heavy electron, is the weight of 200th the width of the mass of a proton. So there's a lot of things to do with it, and in quantum mechanics you've got to get used to it. The heavier it is, the smaller it is. So it's actually, in physical size, smaller than an electron. So that's a bit hard to get your mind about. And so these are just not normal electrons that sit around your atoms and stuff like that. They're electrons which are streaming from the top of the upper atmosphere and pouring down at very high energy. So you've got a high energy particle. It hits the oxygen and nitrogen at the very surface of the atmosphere, heats it up, smashes it apart, smashes it to smithereens, showers the place with neutrons, blah, all these little bits and pieces. It absolutely blows the matter completely apart. And part of what it does in its downward shower is showers us with high energy muons. Now, the fact that they're high energy is actually rather good, because they dissipate their energy in the roughly 10 to 100 meters beneath the Earth. So that actually means that it could be a lot worse for us if they were low energy. So this is one of the things that high energy X-rays are not as bad as low energy X-rays, which don't reach the film but deposit all their energy in you. So this is why a lot of the way that they cleaned up the X-ray dosage is that they just made sure that they only used imaging X-rays and filtered out everything else. So the muons are coming down to us, and they decay, giving some energy. So what do? Do they explode, or do they give out a light particle? Well, a single electron by itself, from quantum mechanics, as it changes from one form to another, doesn't have a dipole moment, doesn't act as an antenna, doesn't produce light. But that's one of the possibilities for it, but that's an impossibility. So it actually decays something which we call by the weak nuclear force, and that involves a vector boson. We call it W minus vector boson. So it decays and produces an electron via the weak nuclear force, and because it's a weak nuclear force, it's a very slow, by atomic physics or nuclear physics process, it's very slow. So it lasts for 2.2 microseconds, which is not very long in our space, but in terms of nuclear physics, that's a very, very long time. So you've got your muon, so it's MUON, and it decays by producing an anti-neutrino, Muon Neutrino, so it's a special type of neutrino, and then produces a vector boson, which doesn't travel very far, and that boson, which has got charge, carrying charge away with it, then decays very quickly into it would decay into a actual decays into the following products. It decays into a neutrino, a muon neutrino, and a vector boson, which is a W minus. It's got its line travelling for some reason has a dashes in a Feynman diagram, and that vector boson, which I suppose you could say is a force carrying a thing. It's a gauge boson that then decays into a electron and an anti-electron neutrino. And I've just got to remember which is you get two neutrinos produced, and one is a muon neutrino and an anti-electron neutrino. I'm trying to see this in my head, and an electron. So what happens is that, as far as we're concerned, the neutrinos go off into space. This is something else I haven't talked to you very much about. This muon will travel through a series of stuff, hang around actually being very small, very charged, will actually, it's got this great thing that it penetrates material, so electrons are not as massive, and so they get deflected very quickly by weak nuclear fields and just bend around and lose their energy really quickly. This is more like a big cannonball, so an electron's more like a shuttlecock, and this is more like a cannonball going through, and it does get deflected when it almost hits or actually goes through a nucleus. It will get this origin will get neglected. So like shuttlecocks will just say, if you've got this suppose in my mind I've got this wooden hold up shack on a hill, and you're trying to see if bad guards are in it, you can either throw just mild bundles of shuttlecocks at it and they will bounce off, or you can fire a cannon through it, and the cannon will either go straight through most of it, and because it's more massive, it's got more momentum in it, or it will actually just bend around when it goes really close to a very heavy nucleus. So this is what we're talking about muons. So this is getting back to the idea that ordinary matter, in your average day, you've got at any one point in time a fair number of these muons going through, and they just go through, rattle around your DNA, sort of decay you a little bit. Sort of muons are not all that much, but they're very interesting things. And so you have a Muon Detector, which is something I'd love to know more about. I might ask my mates up at Lucas Heights, or mates down at Lucas Heights, in a suburb of Sydney. We've got a nuclear reactor, and suburbs are growing either side of it, so it's pretty interesting. And they're making that. So what's happened is that they've built these residential areas near it, and now people are complaining that there's a nuclear reactor there, which is rather interesting. So these muons are penetrating from outer space. Well, they're not coming from outer space, they're coming from the upper atmosphere, from the outer space cosmic rays hitting us, high energy particles. So we've got a particle accelerator for free, which is the universe, and we're the target of it. And we're protected by the atmosphere, but not quite these muons. come through and pervade deep inside them, and they are a type of electron. So you've got your electron, your muon, and your, I think it's tau. Tau is even heavier. I'd hate to think how heavy that is. But these muons are an excited vibration in the leptonic field. I'm just trying to sort of go back and make sure that I don't mix my analogies and mix my analogies of something which is say like a hydrogen atom, which has got fields which you can see how a muon actually gets excited. It's got no spatial extent or structure, so it's one of those things which are going to be hard to understand. I suppose you have to really get in. It's a prediction of something called the standard model. So they made a few predictions, and the standard model produced the 3 generations. So you get 3 generations of quark, up and down quark, and then you've got electrons and neutrinos. That's 2 by 2, and then 3 generations up. Why there's just 3 generations is to do with S3 symmetries, the symmetries going across. And so the muon is a heavy electron, and it's something around us a lot more. So you get muon is actually something in our real world, whereas no sort of decay. You never see this 2 quark particle. So a 3 quark particle is a proton or a neutron. A 2 quark particle is a meson, and the 2 particle was predicted first that you could have a 2-part quark particle. They've all got to have colour white, so you have blue and anti-blue together. So they're actually a particle which obviously is not going to live too long because it's got its matter and antimatter composite. So they found the meson, and they were called mesons, and then they found the mu particle just streaming out of nuclear reactors. So you can make buckets and buckets of muons just by firing your particles and smashing apart molecules, apart your targets, similar to what happens in the upper atmosphere. It's a big accelerator, and you produce something. I don't know how well you produce it. You make a lot of them, you detect them. Sort of they're like the cockroaches of the muons are like the cockroaches of the particle physics world, in terms of there's just buckets of them produced. Oh, good God, like they're infesting. And so you could think that I could make a big muon beam. People haven't, and I think it's because you get so many muons for free coming around the place. Oh, not bloody muons again. And so muons were originally called meson. They thought they were meson, and then they realised they weren't. And so they dropped the meson part, and then it's just called a mu, and so they just add the mu and the on together to drop the meson parts. And so this is a bit confusing for me, because I'm a bit dyslexic. I read one article about mesons, the next article about muons, and it took me a while to realise that they were separate words. But there you go. That's a long time ago. First read about. What on earth could we do with muons? So there's 2 things we can do with muons. We can make muonic matter, that is, knock out an electron and stick a muon in there for a little while and observe a little bit of muonic matter for the 2.2 microseconds while it exists. And in that 2.2 microseconds, a muonic hydrogen or muonic deuterium, or definitely tritium, because the muon is heavier, it's actually smaller, so the actual molecule it makes is small, and it's actually it brings your 2 molecules. It's got such a small bond length, it's actually brings the hydrogen or the 2 deuteriums close enough together for fusion, so you can get muonic fusion. So you get some deuterium, and you deuterium and tritium gas, and you fire muons into it, you'll get a bit of fusion going on. But I think there's these parasitic decay paths, which means this is not God's gift to. God's given us a lot of things, but He hasn't given us muonic fusion. It doesn't last as a parasitic effects which slow it down, which means that you just can't get a muon beam, fire it into your deuterium and power your city with it. You can't do that. But so that's really interesting. The other thing is that muons are a proton probe, because believe it or not, in quantum mechanics there are no surfaces, and the electron can exist and does exist quite happily through the proton. So if you've got the electron cloud barrier, it is the cloud, which is not the correct term for it, but your probability or the wave function. The wave function is maximum probability in the actual centre of the nucleus. Now, because the electron's so big, it actually spends very little time in the nucleus. But a muon is a different case. It's about a factor of 10 times wider than the nucleus. So if you've got your if you can imagine a proton the size of, I'm trying to think of something, a ball which is 10 centimeters across. I can have I'm just trying to think. It's sort of like ping pong ball to volleyball size. The ping pong ball is the size of your proton. The muon is, rather than the size of your basketball court, is the size of your small basketball. Or I'm just doing this off the top of my head to try and produce this into scales, because I've got the scales mathematically in my head. So it's in that small, and you realise that a lot of that muon is actually inside the proton. And the proton is inside the muon. They're waves, and they go through each other. And this causes a shift in the spectra that you would expect out of it, because some of the electron is not actually being pulled centrally, it's actually being pulled out. So there's actually no electric field in the centre of a proton. Try and get that into your head. So the electron actually gets a little bit of a lift, a reduction in the electric field, being actually inside the proton. That's sort of outsmarting it in an amazing way. And that causes you sort of like switch off the electric field for a significant amount, and so it shifts the lines. So you can actually use these lines to actually measure. We know the size of the muon, because that's pretty easy. You got the mass of the muon, the lifetime of the muon, and so that gives you the size of the muon. And so there you go. You can actually find the size of the charge radius of the proton, which is a very interesting thing to see, and to fully understand that. The final application of muons, which is coming out recently, since I sort of was looking at it and just recently read back. So if you can imagine, I was teaching away for a couple of years, read about muons, didn't very busy, then had this little bit of a break where I'm just rebooting everything, remembering everything. It's a bit like going up to a door with something written on it. There's something I had something written on it. You dust it off, and you open it up, and you go through the archives, and you say, it's sort of, you can't remembering it, but you can remember it, but you can't remember how you remember it. But you've got this great thing, and I really want to understand it a bit better. Basically, they can see a muon decay, which is okay. So a muon bounces around, it slows down for a certain amount. So I should imagine you can eliminate direct muons from outer space. You can use the lazy muons, which are about to come out and decay. I think they will decay. They've famously got deferred decay due to special relativity, but they'd get into your detector, and you'd be able to work out from the detector where it came from. So you've got a detector, this detector, and you can actually see muons appear to come from an object. So what's happened is the object itself, like I've got this orange tree in front of me, I've got the air. Muons wouldn't come from the air as a dense, but the muons would actually hook around the proton, come into my detector from a particular direction, but to tell you that muons come from that direction. So I could, if I had a muon detector, I could roll it past, and I could see, there's an orange in that direction, and then from another angle, and there's an orange in that direction. And this process called computer tomography, CT scan. So you go into CT scan, you can actually use, and they are using muons to detect these unfathomable things, these huge mega objects. There's various talks, and I have to read how much this is going. But this is an ideal concept. So people are using it to look for the magma chambers in mountains. Now, I don't know how that could be done, but there's much more realistic things for finding the objective is if there's uranium in it, because uranium's got a much higher nucleus, a much greater cross section for really giving a good old scattering to those muons coming in, which come into your detector, and you can work it out then. So from what I can read, there's at least talk, but not papers I've read in the popular science, of these muon CT scans. You have your muon detectors, put half a dozen muon detectors around a mountain or a nuclear reactor or a ship, and you can tell whether that ship's got a big lump of uranium in it. The magma chamber is empty or it's full. I think that's one of the things you'll be able to tell if there's a big void. And so back in the day, they were getting intense gamma ray sources to get through the pyramids of Giza, and now they're getting Muon Detector. So that's really a rather interesting aspect to it. And it takes quite a bit to understand how something which has no structure in it can have an excited state. You really begin to get beyond the bounds of human understanding. I mean, it's even the leptons with the S2 symmetry, the 720 degrees spin up, spin down, is hard to imagine. And of course, I think this will be an interesting thing. Neutrinos do carry spin. Neutrinos have to carry spin. They're in the spin half aspect. And so that's something pretty profound. Something which weighs nothing, travels at the speed of light, can actually travel through a light year of lead before it interacts. Carries spin, angular momentum with it, but thinking about it has to carry spin. That is because a neutron will decay to an electron, and a neutrino. So the neutrino has to have spin with it. It's quite an interesting thing. But then that's carried that decay, a neutron to a proton. Is that the weak nuclear force? I think it is the weak nuclear force, and the weak nuclear force obviously occurs at a much longer time period. So neutrons decay in in a quarter of an hour, whereas muons decay in 2.2 microseconds. That's interesting. The symbol for that, I conceive myself 2.103 in my head. I can see that, but I can't. And that would be 2.1, so it must be 2.2 somehow. So I'll just read up how that's done. I thought I'd share that with you and put this away as a quick podcast to clear it off my brain and clear it out there. Thanks a lot for listening. Another podcast, another story comes to a close. It's been a pleasure sharing this moment in time with you. May you discover truly amazing things, understand them, and tell others. Thanks for listening.